Look up at the night sky. What do you see? Pinpricks of starlight, perhaps the serene glow of the moon. It feels peaceful, almost quiet, but this tranquility is a magnificent illusion. Every second, an invisible storm rages overhead, a silent, ceaseless downpour of the most powerful light the universe can produce. This is the cosmic gamma-ray background, a faint, omnipresent fog of high-energy radiation that bathes the entirety of space. It's not a light you can see with your eyes, but it's there, a whisper from the most violent and explosive corners of reality, and it holds within its faint signal some of the greatest secrets our cosmos has yet to reveal. Think of it like this: you're trying to listen to a faint, beautiful melody playing from a distant room, but you're standing in the middle of a stadium roaring with the static of a million unseen voices. That's the challenge scientists face. This gamma-ray static isn't just noise, it's the combined echo of every catastrophic event happening across the universe, all talking at once. It's the afterglow of titanic stellar explosions, the furious jets from supermassive black holes, and possibly the ghostly signature of dark matter itself annihilating in the void. This background is the ultimate cosmic palimpsest, layer upon layer of history written in a language of pure energy, and we are only just beginning to learn how to read it. So, how do we begin to untangle this cosmic cacophony? In this journey, we will dive deep into 25 specific, mind-bending mysteries concealed within this pervasive glow. We will explore questions that push the very boundaries of physics. What catastrophic events are contributing to this eternal hum? Could some of this radiation be the long-sought proof of dark matter particles? Are we seeing the echoes of ancient, unimaginably powerful phenomena from the dawn of time? This is more than a tour of unsolved puzzles. It's an invitation to witness the forefront of discovery, to peer into the fundamental forces that have shaped everything we know. The story written in gamma rays is the story of the universe at its most extreme, and it's a story we are only starting to understand. Our first and perhaps most foundational mystery begins with the simple question of where this glow even comes from. If the night sky were a canvas, the stars and galaxies we see would be distinct brushstrokes, but the gamma-ray background is different. It's like a wash of faint color applied evenly across the entire surface. This diffuse nature is the core of the puzzle. It wasn't discovered by looking at one specific spot, but by patiently mapping the entire sky and realizing that the gamma-ray signal persists everywhere, even in the seemingly emptiest patches of space between known galaxies. The key instrument that revealed this hidden landscape to us is the Fermi Gamma-Ray Space Telescope, an observatory that has been orbiting our planet since 2008. Fermi acts like a pair of ultra-sensitive sunglasses, allowing us to see the universe in the extreme energy of gamma rays. As it scanned the heavens, it became clear that even after you subtract the light from every identified source, every pulsar, every flaring galaxy, every gamma-ray burst, a persistent, uniform fog remains. It's the cosmological equivalent of hearing a constant hum in a quiet room after you've turned off all the appliances you can think of. This immediately rules out a straightforward explanation. It can't simply be the combined light of known types of gamma-ray emitters, because those create a lumpy, pointillistic map. The smoothness tells us we are dealing with something far more numerous and widespread. Sources so incredibly distant or faint that our telescopes cannot pick them out individually. They blend together into a cosmic static. So, what are these unseen contributors? One compelling theory points to an unresolved population of blazars. A blazar is a galaxy centered on a supermassive black hole that is shooting a jet of radiation directly at us. Think of each one as a lighthouse beam aimed right at Earth. Now, imagine countless, much fainter versions of these lighthouses scattered across the far reaches of the universe. Their individual beams are too weak for Fermi to distinguish, but together, their combined, smeared-out light could very well be the source of this pervasive glow. But there is another, even more tantalizing possibility woven into this signal: dark matter. We know this mysterious substance makes up about 85% of all the matter in the cosmos, yet it refuses to interact with light, making it effectively invisible. However, some leading theories suggest that when two dark matter particles collide, they could annihilate each other, transforming into a shower of particles that includes gamma rays. If this is happening throughout the vast halos of dark matter that surround galaxies and permeate space, it would produce a faint, widespread emission, a perfect match for the diffuse glow we observe. The challenge is monumental. Distinguishing between the gamma rays from a trillion faint blazars and the gamma rays from the annihilation of an invisible substance requires painstaking statistical analysis. It's like trying to determine if the background noise in a city is caused by millions of distant conversations or by the hum of the electrical grid itself. Unraveling this first mystery is not just about cataloging cosmic events. It's a direct investigation into the fundamental ingredients of the universe itself. Building directly on the idea of unresolved sources, we arrive at our second great mystery, one that spotlights some of the most violent and brilliant engines in the cosmos. Could the answer to the background's origin be as simple as adding up the light from countless blazars? A blazar is the core of a distant galaxy, but to call it simply a galaxy is a profound understatement. At its heart sits a supermassive black hole, often weighing billions of times the mass of our Sun. As vast amounts of matter spiral relentlessly toward this gravitational abyss, a portion of it is channeled into a pair of jets, twin beams of particles and radiation, that scream away from the black hole at nearly the speed of light. What makes a blazar so special and so blindingly bright to our telescopes is our unique cosmic perspective. One of those jets is pointed almost directly at Earth. We are looking straight down the barrel of the most powerful particle accelerator in the universe. The energy involved is almost incomprehensible. A single blazar can outshine the combined light of every star in its entire galaxy, all focused into the gamma ray part of the spectrum. When Fermi looks at the sky, these objects are the brightest, most obvious features on the map. So, the logical next step is to ask a census question. If we can see the bright, nearby blazars so clearly, surely there must be a vast, unseen population of fainter, more distant ones. Their light, traveling across billions of light-years, would be stretched and dimmed, but their combined, unresolved glow could theoretically paint the entire sky with the uniform gamma-ray fog we observe. It's a compelling and elegant explanation. The background is simply the accumulated whisper of a cosmic choir, too far away for us to hear any single voice. This, however, is where the debate intensifies and the mystery deepens. The critical task for astronomers is to conduct a precise cosmic accounting exercise. They use the number and brightness of the blazars we can see to build a statistical model, predicting how many faint ones must exist just beyond our detection threshold. The pivotal question is this: when you extrapolate this model out to include every possible blazar in the observable universe, does the sum total of their gamma-ray light perfectly match the observed intensity of the background? The answer, frustratingly and excitingly, is not a simple yes or no. Some sophisticated models suggest that blazars could indeed account for the entire signal. They propose a universe teeming with these energetic beasts, their numbers increasing in just the right way at fainter levels to fill in the diffuse glow completely. Yet, other analyses point to a significant shortfall. These studies indicate that even when you add up the maximum plausible number of blazars, there remains a portion of the background flux, particularly at certain energies, that is left unexplained. It's as if you've counted every person speaking in a crowded room, but the volume of the background noise is still louder than all their voices combined. This discrepancy is the heart of the debate, and it points toward the existence of a missing component. The challenge is magnified by an observational blind spot. Our telescopes have a fundamental sensitivity limit. They cannot see the very faintest and most distant of these objects. This is like trying to count stars on a foggy night. You can see the bright ones clearly, but the myriads of faint ones blend into an unresolved haze. Are we missing a specific class of blazar that evolves differently over cosmic time? Or could there be a population of gamma-ray sources that are fundamentally different from blazars, perhaps something we haven't even thought of yet? The inability to directly detect these faint sources means we are forced to rely on statistical inference, a process filled with uncertainty. This ongoing investigation into blazars is far more than a technical argument over numbers. It is a fundamental probe into the population of monster black holes across the history of the universe, and a crucial step in determining if we need to invoke something even more exotic like dark matter to explain what we see. The light from these jets may be illuminating a path toward a much deeper truth. This brings us to one of the most profound and thrilling possibilities embedded within the gamma-ray static, the potential whisper of dark matter itself. While blazars represent known, albeit distant, astrophysical powerhouses, the dark matter hypothesis ventures into the realm of the truly unknown. We have overwhelming evidence that dark matter exists. Its gravitational pull dictates the rotation of galaxies and the evolution of the largest cosmic structures. Yet for nearly a century, it has remained completely invisible, refusing to interact with light in any way we can directly observe. The cosmic gamma-ray background offers a potential backdoor, a way to see the unseeable. The theory rests on a fascinating idea. What if dark matter isn't entirely inert? What if, under the right conditions, it can annihilate or decay? This is where hypothetical particles like WIMP come into play. WIMP stands for Weakly Interacting Massive Particle, and it has long been a leading candidate for what dark matter could be made of. The key word is weakly. These particles would not interact via the electromagnetic force, which is why they are dark, but they might interact through the weak nuclear force or simply through their own gravity. The annihilation scenario is particularly compelling. If two WIMP were to collide, the theory suggests they could obliterate each other, converting their mass directly into energy according to Einstein's famous equation, and producing a cascade of secondary particles, including gamma rays. Since dark matter is thought to form vast, diffuse halos around galaxies and even fill the spaces between them, these annihilations would be happening everywhere all the time, creating a faint, omnipresent glow of gamma radiation, a perfect description of the background we see. Scientists aren't just looking for any random gamma ray, however. They are hunting for a very specific spectral signature. If dark matter is made of a specific type of particle with a specific mass, then the energy of the gamma rays produced from its annihilation would be sharply defined. Imagine tuning a radio. You're searching for a clear, distinct signal at one particular frequency, rising above the static of all the other stations. In the gamma-ray sky, this would manifest as an unexpected bump or a narrow line at a specific energy within the smooth background. Finding such a line would be the smoking gun, a direct fingerprint of the dark matter particle itself, revealing its mass and fundamentally altering our understanding of the universe. The challenge, of course, is monumental and lies in the painstaking work of subtraction. The gamma-ray sky is a messy place crowded with the overlapping signals from blazars, pulsars, and other astrophysical phenomena. Distinguishing a potential dark matter signal from this astrophysical foreground is like trying to isolate the sound of a single, quiet instrument within a full symphony orchestra. Researchers must create incredibly detailed models of all the known sources of gamma rays and subtract their expected contributions from the total signal. Whatever stubborn residue remains could potentially be attributed to dark matter, but this requires a deep understanding of the astrophysical sources themselves, and as we've seen with the blazar debate, our models are not yet perfect. An unexplained signal could equally point to an unknown population of faint galaxies or a new type of cosmic accelerator we haven't yet considered. The search is further complicated by the fact that the predicted dark matter signal is expected to be strongest in regions where dark matter is most densely concentrated, such as the centers of galaxies like our own Milky Way. Scientists therefore perform a kind of cross-check, comparing the gamma-ray background from the general extragalactic sky with the signal coming from the galactic center. If the same spectral signature appears in both, and if it cannot be explained by any known astrophysical source in either location, the case for a dark matter detection becomes immensely stronger. A confirmed signal would be more than just another discovery. It would rank among the greatest breakthroughs in the history of science, finally illuminating the 85% of the universe's matter that has remained hidden since the beginning of time. It would open a direct window into the particle physics of the dark sector, potentially revealing a whole new chapter of fundamental laws. But if the blazing fury of active galaxies isn't enough to fully explain the background, perhaps we need to consider a far more common, yet still powerful cosmic citizen, the ordinary star-forming galaxy. We've been focusing on the universe's most extreme monsters, but what about the collective hum of its countless bustling towns and cities? Galaxies like our own Milky Way are not passive islands of stars. They are dynamic ecosystems where the continuous cycle of birth and death generates its own kind of high-energy signature. The process begins with the most massive stars. These giants live fast and die young, exploding as supernova at the end of their short lives. Each detonation is a cataclysm that not only seeds the galaxy with heavy elements, but also acts as a natural particle accelerator, launching protons and atomic nuclei to nearly the speed of light. These become what we call cosmic rays. Now imagine these ultra-fast particles, these cosmic rays, streaming through the vast clouds of gas and dust that fill a galaxy, the very raw material for new stars. When a cosmic ray proton smashes into a proton within an interstellar gas cloud, the collision can create a short-lived particle called a pion, which almost instantly decays into gamma rays. This process turns the entire interstellar medium of a star-forming galaxy into a diffuse, glowing fog of high-energy light. The more actively a galaxy is forming new stars, the more supernova it produces, the more cosmic rays it generates, and the brighter it glows in gamma rays. It's a continuous cycle of creation and destruction that leaves a distinct energetic fingerprint. So, the question becomes one of cosmic demographics. Star-forming galaxies are incredibly numerous, far more common than the rare and dramatic blazars. It seems almost inevitable that their combined, unresolved light must contribute to the cosmic gamma-ray background. Think of it like the sound of a vast global city. You can easily hear the distinct siren of an emergency vehicle or the roar of a single jet engine. These are the blazars. But beneath those loud, individual noises lies the pervasive, collective hum of millions of cars, conversations, and air conditioners. That constant, low-level hum is the combined output of all the ordinary activity, and it forms the acoustic background of the city. In the same way, the faint gamma-ray light from countless distant, star-forming galaxies should blend together to create a fundamental baseline for the universe. Astronomers have indeed confirmed that nearby star-forming galaxies, like the famous Andromeda galaxy, do emit gamma rays from these processes. We can measure their individual output. The challenge, once again, is extrapolation. Using what we know from local galaxies, scientists build models to predict the total gamma-ray flux from all such galaxies across cosmic history. The results place star-forming galaxies in a fascinating and crucial role. They are almost certainly a significant component of the background, a guaranteed contributor that any complete model must include. However, most estimates suggest that on their own they are unlikely to account for the entire signal. They provide a substantial portion of the cosmic hum, but there seems to be a remaining excess, a residual glow that points to something else. This makes them not a competing explanation to blazars or dark matter, but rather a key piece of the puzzle. A complete understanding requires us to add together the light from active galaxies, the light from star-forming galaxies, and potentially the light from something even more exotic. The quiet, steady work of cosmic rays in ordinary galaxies forms an essential chorus in the universe's grand symphony, a background rhythm against which the solos of more violent events are played. Moving beyond the steady glow of galaxies, we must now consider the most violent singular explosions known to exist, gamma-ray bursts. If the universe's everyday activity creates a persistent hum, then GRBs are the equivalent of cosmic fireworks, sudden, blindingly bright flashes that, for a few fleeting seconds, can outshine every other source of gamma rays in the sky combined. These are not the orderly jets of blazars or the distributed glow of cosmic rays. These are catastrophic detonations signaling the birth of a black hole or the collision of ultra-dense stellar corpses. The sheer energy released is staggering, and it raises a fascinating question. If these events are so brilliant, could the faint, collective afterglow of every GRB that has ever occurred, spread across the entire history of the cosmos, be adding to the background static we observe today? To understand how this could work, picture a vast, dark plane. Every so often, a massive firework explodes high in the sky, creating an intense, momentary blaze of light. Now imagine that these fireworks have been going off for billions of years all across the plane. While the initial flash of each one is brief, a faint, lingering smoke or ember might persist for a short time afterward. If the fireworks are frequent enough and spread across a long enough timeline, the combined glow from all their lingering afterglows could create a permanent, dim illumination that hangs over the entire landscape. This is the essence of the hypothesis for GRBs. Each burst has a distinct phase called the afterglow, which occurs immediately after the initial explosion. As the relativistic jet slams into the surrounding interstellar material, it creates a long-lasting emission that fades across the spectrum, from gamma rays down to X-rays and visible light. It is this fading high-energy tail that could, in principle, contribute a diffuse and steady component to the gamma-ray background. The crucial variable here is the rate of these events across cosmic history. How many gamma-ray bursts have there been? Our telescopes, like NASA's and Neil Gehrels Swift Observatory, detect roughly 1 GRB per day. But this is a local census. We are only seeing the exceptionally bright nearby bursts. For every one we detect, there must be countless more that are too distant, too faint, or pointed in the wrong direction for our instruments to catch. The universe is vast and old, and if GRBs were common in the early universe, their total number could be astronomical. Researchers build complex cosmological models that account for the evolution of stars over time, predicting how often the massive stars that produce long GRBs were born, and how often neutron stars merged in the ancient cosmos. These models simulate a universe filled with GRBs, calculating the combined light from all their afterglows at every point in time, and summing it up to predict the total diffuse glow we should see today. The results of this cosmic accounting are intriguing but inconclusive. Some models suggest that the integrated emission from GRB afterglows could indeed make a noticeable contribution to the background, particularly at specific energy ranges. However, most studies indicate that it is unlikely to be the dominant source. The problem is one of duration versus frequency. While each GRB is incredibly luminous, its afterglow at gamma-ray energies is still relatively short-lived. To create a persistent, uniform fog, you would need an immense number of bursts happening almost continuously across the universe to ensure their fading lights always overlap. The current best estimates suggest that while GRBs add another layer to the cosmic chorus, they are probably not the lead singer. Their contribution seems to be a significant part of the mix, but there remains a portion of the background that their light alone cannot explain. This investigation is fraught with profound uncertainties. Our understanding of the true GRB rate in the early universe is limited, and the physics of their afterglows is complex. A change in the assumptions about how efficiently these explosions produce gamma rays, or a discovery that there was a previously unknown population of faint, long-duration bursts in the first billion years after the Big Bang, could drastically alter the calculations. The unresolved light of gamma-ray bursts represents a tantalizing piece of the puzzle, a testament to the universe's most violent moments. Their potential contribution reminds us that the faint glow we see today is a palimpsest written not just by steady processes, but by the accumulated echoes of ancient cataclysms, each one a brief scream of energy that has faded to a whisper across the aeons. While the universe's grandest explosions capture our attention, some of the most efficient and enduring particle accelerators are operating on a more local, galactic scale. This brings us to the fascinating interplay between pulsar wind nebulae and supernova remnants, two deeply connected phenomena that are fundamental producers of the cosmic rays which ultimately generate gamma rays. To appreciate their potential role in the cosmic background, we must first understand the incredible engine at the heart of a pulsar wind nebula. Imagine the core of a massive star that has collapsed not into a black hole, but into a city-sized sphere of pure neutrons, a neutron star. This object is so dense that a single teaspoon of its material would weigh billions of tons, but the real magic happens with its spin. As the star collapses, it conserves its angular momentum, spinning up to incredible speeds, sometimes hundreds of times per second. This rapidly rotating neutron star becomes a pulsar, generating an immense magnetic field trillions of times stronger than Earth's that acts like a colossal dynamo. This magnetic dynamo pulls charged particles from the surface of the neutron star and accelerates them to nearly the speed of light, creating a powerful wind that streams outward. This wind, however, doesn't just fly off into empty space. It slams into the slower-moving material ejected during the original supernova explosion, creating a massive, expanding bubble known as a pulsar wind nebula. Inside this bubble, the particles are trapped by magnetic fields and undergo a process called synchrotron radiation, emitting light across the spectrum, including high-energy gamma rays. The Crab Nebula is the most famous example of this. Its ghostly, filamentary glow in visible light is just part of the story. In gamma rays, it is one of the brightest steady sources in the sky, a testament to the ferocious particle acceleration happening within. These nebulae are not just temporary features, they can shine brightly for thousands of years, acting as long-lasting lighthouses of high-energy physics within our galaxy. The story of cosmic rays, however, begins with an even more dramatic event, the supernova remnant itself. When a star explodes, it hurtles its outer layers into space at tremendous speeds, creating a vast, expanding shock wave. This shock front is a natural and incredibly efficient particle accelerator. As protons and other atomic nuclei get caught in this moving wall of gas, they are bounced back and forth by magnetic fields, gaining a little more energy with each crossing. Over time, they are boosted to the phenomenal energies that characterize cosmic rays. Once these particles are accelerated, they too can collide with the ambient gas in the remnant, producing gamma rays through the same pion decay process we see in star-forming galaxies. So, a supernova remnant is often a two-stage factory. First, it creates the cosmic rays, and second, it provides the environment for those rays to generate the gamma ray light we can detect. The crucial question for the cosmic gamma ray background is whether the combined light from these sources, both within our Milky Way and in distant galaxies, adds up to a significant contribution. Within our own galaxy, we can study individual pulsar wind nebulae and supernova remnants in exquisite detail. We know they are prolific gamma ray emitters. The challenge, as with blazars and star-forming galaxies, is in the extrapolation. Can we use what we see locally to build a model for the entire universe? The answer is complex. These sources are inherently local in a cosmic sense. They are associated with the life and death of stars within the galactic disk. While every galaxy likely has its own population of these objects, their gamma-ray emission is largely contained within their host galaxies. Unlike the jet from a blazar that is beamed directly across the universe, the gamma rays from a pulsar wind nebula or supernova remnant radiate in all directions, and much of that light is absorbed or scattered within its own galaxy. Therefore, the total extragalactic background light from these sources depends entirely on the cumulative output of every galaxy like our own. This makes them a component of the larger category of emission from star-forming galaxies rather than a separate dominant class. Their significance lies in their efficiency. They demonstrate the specific, powerful mechanisms by which ordinary galactic processes can generate the high-energy particles that fill the universe. While they may not single-handedly solve the background puzzle, they are essential pieces of the machinery. Understanding them helps us refine our models of the total gamma-ray output from a typical galaxy, bringing us closer to a complete inventory of the cosmos's invisible light. Now, let's expand our gaze from individual galaxies to the colossal metropolises of the cosmos, galaxy clusters. These are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, all swimming in an immense sea of superheated gas known as the intracluster medium. This gas is so hot that it glows in X-rays, but the question for us is whether it also leaves a faint signature in gamma rays. The fascinating possibility arises not from the galaxies themselves, but from the vast, invisible ocean that surrounds them. Within a galaxy cluster, the turbulent motions of galaxies and the immense gravitational forces generate powerful magnetic fields and can accelerate particles to relativistic speeds, creating a population of cosmic rays that become trapped within the cluster's gravitational grasp. These cosmic rays, confined for billions of years, continuously collide with the protons in the hot intracluster gas. Each collision can produce a neutral pion, which then decays into two gamma rays. This process would paint the entire volume of a galaxy cluster with a faint, diffuse gamma ray glow. Because clusters are so enormous, spanning millions of light years, their combined emission, if we could detect it from such distances, might contribute a subtle but widespread component to the cosmic background. It's the energetic hum of the universe's greatest cities, a signal of the dynamic life within these vast structures. This idea connects directly to an even grander cosmic process, the very formation of the large-scale structure of the universe. The distribution of matter we see today isn't random. It forms an intricate cosmic web, a network of filaments where galaxies and clusters are strung like pearls on a string, separated by enormous voids. The assembly of this web was a violent and energetic affair. As dark matter pulled ordinary matter into these filaments, gas fell inward under immense gravitational pressure, creating colossal shock waves known as accretion shocks. These are not the shocks of a single supernova, but titanic walls of energy larger than galaxy clusters themselves, wherein falling gas was heated to temperatures of tens of millions of degrees. At these vast frontiers, particles could have been accelerated to extreme energies, generating cosmic rays on a cosmological scale. And just like in galaxy clusters, those cosmic rays would have interacted with the surrounding gas to produce gamma-ray radiation. The tantalizing implication is that the cosmic gamma-ray background might not be perfectly smooth. It could contain an incredibly faint web-like imprint, a ghostly tracing of the cosmic scaffolding itself. This would be the ultimate signature of structure formation, a direct glimpse into the energetic processes that built the universe from a nearly uniform soup after the Big Bang into the complex tapestry we observe today. Detecting such a signal, however, is at the very limit of our capabilities. It would require exquisitely sensitive maps of the gamma-ray sky, and sophisticated statistical techniques to tease out a pattern that is woven into the background noise. A confirmed detection would be revolutionary, providing a completely new way to study the growth of cosmic structure and probe the physics of the intergalactic medium on the largest scales. It would mean that the gamma-ray background is not just a fog, but a reflection of the universe's very architecture. Leaving behind the colossal structures of the modern universe, our investigation into the gamma-ray background now takes us back to the very beginning, to the first moments of creation, where we encounter two of the most speculative and mind-bending possibilities. These are ideas that stretch the limits of theoretical physics, proposals that, if proven true, would revolutionize our understanding of reality itself. The first of these exotic candidates takes us to a time before the first stars, before the first atoms, to a universe that was a seething, dense soup of energy. In these initial chaotic instants, tiny fluctuations in density could have been so extreme that regions of space simply collapsed under their own gravity, not forming from dying stars but being born directly from the fury of the Big Bang. These are primordial black holes, and they could be everywhere, potentially constituting a significant portion, or even all, of the dark matter. The connection to the gamma-ray background lies in their eventual spectacular demise. Stephen Hawking theorized that black holes are not entirely black. Due to quantum effects near their event horizons, they should slowly lose mass and evaporate over astronomical timescales. For a stellar mass black hole, this process is unimaginably slow. But for a primordial black hole with the mass of a small asteroid or even a mountain, the story is different. Their evaporation would be accelerating, and the final moments would be anything but quiet. As a primordial black hole nears the end of its life, its temperature skyrockets, and it would erupt in a final, brilliant flash of radiation, a burst of particles and, crucially, gamma rays. This event would be a miniature gamma-ray burst, a tiny, high-energy firecracker popping off in the void. Now, imagine a universe filled with countless such black holes, all evaporating at different times across billions of years. The combined effect of these countless final flashes could create a faint, diffuse, and steady rain of gamma radiation, a contribution to the background that is both ancient and ongoing. The challenge, of course, is that no one has ever conclusively detected a primordial black hole or its evaporation. We are searching for the ghostly signature of objects that may have formed in the first second of time, a hunt that requires looking for a specific, predicted signal hidden within the cosmic noise. Even more speculative than primordial black holes is the concept of cosmic strings. These are not strings in any ordinary sense. They are hypothetical one-dimensional defects in the very fabric of spacetime itself. Think of the universe as it cooled from an ultra-hot, symmetric state after the Big Bang. Much like water freezing into ice crystals can develop cracks and fissures, the transition of the fundamental fields of the universe could have created incredibly thin but unimaginably dense filaments of energy cosmic strings. A segment of string just a mile long might contain more mass than our entire sun. These entities would be truly alien, narrower than a proton, but stretching across the entire observable universe, vibrating and oscillating at near light speed. The gamma-ray connection emerges from the dynamics of these vibrating strings. As they oscillate, they can develop kinks or cusps where sections of the string collide with themselves. At these points, the immense energy density of the string could be released in a powerful burst of high-energy radiation, including gamma rays. In a more dramatic scenario, if two segments of a string cross, they could reconnect and snap, releasing a tremendous amount of energy in the process. If cosmic strings exist, these energetic events would have been happening throughout cosmic history. The gamma rays from these snaps and oscillations spread across space and time would blend together into a diffuse background glow. The signal would be incredibly faint, but potentially distinguishable from other sources by its unique statistical properties. While the existence of cosmic strings remains entirely theoretical, their potential detection through the gamma-ray background would be one of the most profound discoveries in science. It would provide direct evidence for grand unified theories of physics and offer a tangible relic from a time when the forces of nature were one. These two ideas, primordial black holes and cosmic strings, represent the ultimate frontier in this investigation. They remind us that the faint glow we see might not just be from stars and galaxies, but from the deepest, most fundamental processes that shape the cosmos at its birth. Up until now, we've been focused primarily on the total amount of light and the possible identities of the sources that create this pervasive gamma-ray fog. But to truly solve this cosmic mystery, we need to shift our perspective and ask a different, more subtle question. How is this light arranged? This brings us to a critical and deeply revealing aspect of the background known as anisotropy. In simple terms, anisotropy refers to the fact that the gamma-ray fog is not perfectly smooth. If you could look at it with impossibly sensitive eyes, you would notice incredibly faint, patchy variations in its intensity, bright spots and dim spots scattered across the sky like a subtle texture on a vast canvas. It's the difference between the uniform glow of a perfectly overcast sky and the dappled light filtering through a layer of thin, patchy clouds. These minute fluctuations are not random noise, they are a treasure trove of information. They hold the key to distinguishing between the different candidate sources, because each type of source would clump together in the sky in its own unique way. Imagine you're listening to that crowded room again, but this time you have a sophisticated sound map that shows you not just the overall volume, but where the sound is coming from. The loud, individual voices of nearby blazars would create distinct, sharp points on the map, but the combined murmur of a large population of distant, unresolved blazars would create a specific kind of granularity, a certain statistical pattern of clustering that depends on how these objects are distributed throughout the universe. Dark matter, on the other hand, would produce a very different pattern. Since dark matter is thought to form an immense cosmic web, its gamma-ray signal would be strongest along the filaments of this web and around massive galaxy clusters, creating a much larger scale, fainter pattern of variation across the sky. By meticulously mapping these anisotropies, astronomers are essentially taking a fingerprint of the hidden universe. The technical challenge involved in this work is staggering. The variations we're trying to measure are exquisitely subtle, buried deep within the noise of the detector itself and the overwhelming signal from bright, individual sources within our own galaxy. The first and most crucial step is perhaps the most painstaking: cleaning the data. Researchers using the Fermi Large Area Telescope data must first remove the gamma rays coming from all the known point sources, every identified blazar, pulsar, and gamma ray burst. Then they have to subtract the bright, diffuse emission from our own Milky Way galaxy, which is like trying to see a faint, distant pattern projected onto a brilliant, swirling backdrop. Only after this intensive cleaning process do they finally have a map of the truly extragalactic gamma-ray background, and can they begin the delicate task of searching for its intrinsic texture. What have these detailed analyses revealed? The latest maps confirm that the background is indeed anisotropic. It is not perfectly smooth. There is a detectable level of clustering, a clear sign that the unresolved sources are not distributed completely randomly in space. The characteristics of this clustering are particularly telling. The pattern appears to be consistent with what we would expect from a population of sources that are themselves clustered, much like galaxies are clustered in the cosmos. This finding is a significant blow to the idea that dark matter annihilation could be the sole source of the background. Because dark matter is so much more diffusely distributed than galaxies, its signal would be expected to be far smoother on the angular scales that have been studied. The observed anisotropy points strongly toward a dominant contribution from astrophysical sources, objects that trace the visible matter in the universe. However, the story is not that simple. While the anisotropy data rules out dark matter as the primary source, it doesn't perfectly match the predictions for blazars alone either. The level of fluctuation seems to be a bit lower than some models anticipated. This suggests that the real picture is a complex mixture. The background is likely a composite signal, with blazars providing the dominant clumpy component, but with another, smoother component diluting the fluctuations. This smoother component could be the collective light from the much more numerous and widely distributed star-forming galaxies, or it could even include a small, residual contribution from the truly diffuse dark matter. The anisotropy problem, therefore, is not about finding a single culprit, but about precisely measuring the recipe. It's a statistical exercise in cosmic cooking, determining exactly how much of each ingredient, how many blazars, how much galactic emission, and perhaps a pinch of dark matter, is needed to produce the specific texture of the gamma-ray sky we observe. Each new, more sensitive map brings us closer to cracking this code, turning a faint, uniform fog into a detailed blueprint of the universe's hidden structure. Moving beyond the subtle patterns in the sky's brightness, we encounter a puzzle written not in space, but in energy itself. This is the mystery of the spectrum, a plot that charts how the intensity of the background changes with the energy of the gamma rays. If the anisotropy maps are like a weather map showing the fog's patchiness, the spectrum is like analyzing the chemical composition of every droplet within that fog. It reveals a signature that is both revealing and deeply perplexing, because its specific shape doesn't neatly align with what we'd expect from any one type of source. It's a cosmic cocktail, and we're trying to identify every single ingredient just by tasting the final mix. Imagine you're trying to identify a group of distant musicians by listening to the combined sound they produce. A trumpet has a bright, piercing sound, a cello produces a rich, deep tone, a drum provides a sharp, percussive beat. Each instrument contributes to specific parts of the overall soundscape. The gamma-ray spectrum works in a similar way. Different astrophysical processes produce gamma rays with distinct energy signatures. For example, the gamma rays generated when cosmic rays collide with gas clouds, the pion decay process, create a spectrum with a very characteristic bump at a specific high energy. In contrast, the radiation from the blazing jets of a blazar, which is produced by electrons spiraling in magnetic fields, creates a smoother, power law spectrum that slopes downward in a predictable way as the energy increases. The spectrum, therefore, acts as a unique fingerprint for each type of source. When scientists plot the measured spectrum of the cosmic gamma-ray background, they are confronted with a curve that is deceptively simple in its smoothness, yet devilishly complex in its implications. It's a nearly featureless power law, but one with subtle bends and a specific steepness that no single population of objects can perfectly reproduce. This is the heart of the energy spectrum puzzle. If blazars were the sole contributors, the spectrum would have one particular slope. If star-forming galaxies dominated, we would expect a different slope, perhaps with that telltale pion decay bump. The actual measured spectrum lies somewhere in between these predictions. It's as if you combine the sound of the trumpet and the cello, but the resulting melody has a tone that isn't quite right for either instrument alone, suggesting a third, unknown instrument is also playing. This mismatch forces astronomers to become master mixologists of the cosmos. They create sophisticated models that combine the expected spectra from blazars, star-forming galaxies, and other potential contributors in varying proportions. The goal is to find the precise recipe that, when all the ingredients are blended together, reproduces the smooth curve we observe. The challenge is that the models are only as good as our understanding of the ingredients. Perhaps we don't fully understand the true spectrum of distant, faint blazars. Maybe their jets behave differently over cosmic time. Or the pion decay bump from star-forming galaxies could be smeared out and hidden because we're seeing the combined light from galaxies across billions of years of evolution, each at a different distance, whose light is redshifted by different amounts. This cosmological effect stretches and distorts the individual spectral fingerprints, making them harder to identify in the composite signal. The most intriguing possibility, however, is that the spectrum's peculiarities are hinting at a missing ingredient, a source of gamma rays that we haven't yet accounted for. This is where the puzzle connects back to the most exotic hypotheses. For instance, the predicted spectrum from certain types of dark matter particle annihilations can have a very specific shape, often characterized by a sharp cut-off at high energies corresponding to the mass of the particle. The fact that the observed background spectrum shows no such obvious sharp feature has actually helped physicists rule out entire classes of dark matter candidates. Yet, more subtle contributions from dark matter could still be hiding within the smooth curve, subtly altering its slope in a way that is only apparent when every other astrophysical source has been perfectly modeled. The spectrum, therefore, is not just a tool for identifying what's there. It's also a tool for excluding what cannot be there, narrowing down the possibilities for both particle physics and astrophysics. Unraveling the energy spectrum puzzle requires a multi-pronged approach. It demands better observations from future telescopes that can peer deeper into the gamma-ray sky with higher resolution. It also requires more precise theoretical models of how particle acceleration works in environments from blazar jets to supernova remnants. Every slight improvement in our understanding of a known source refines the recipe and tightens the constraints on what remains unexplained. The spectrum is a fundamental clue that cuts across all the other mysteries. It is the hard data that any successful theory must ultimately explain. Its smooth, unassuming curve is a silent challenge to our understanding of the high-energy universe. A reminder that the final answer will likely be a complex harmony of many different voices, rather than a solo performance from a single cosmic phenomenon. But to understand the full journey of this light, we must consider the cosmic medium it travels through. The universe is not a perfect vacuum for gamma rays. It's filled with a faint, accumulated glow of starlight from every star that has ever shone. This is the extragalactic background light, or EBL. Think of it as a cosmic fog, a permanent twilight created by the combined photons from all the galaxies across cosmic history. It's the total fossil record of starlight, and for a high-energy gamma ray, this fog is anything but transparent. When a gamma-ray photon, traveling for billions of years from a distant blazar or galaxy, encounters a lower energy photon from this EBL fog, they can annihilate each other. This process, known as pair production, transforms the two photons into an electron and a positron. The highest energy gamma rays are the most vulnerable, as they are more likely to find a suitable partner photon to interact with. It's a cosmic game of chance, where the odds of a gamma ray making it to our telescopes decrease dramatically the farther it has to travel and the higher its initial energy. This absorption effect acts like a filter, systematically removing the most energetic photons from the most distant sources and effectively putting a ceiling on the gamma ray energies we can observe from the early universe. This presents a fascinating complication, but scientists have brilliantly turned this obstacle into a powerful tool. The degree of absorption we see depends directly on the thickness of the EBL fog. If the fog is dense, more high-energy gamma rays get absorbed. If it's thinner, more get through. By carefully measuring how the gamma ray spectrum from distant sources is softened or attenuated, how the highest energy part of the signal is weakened, astronomers can work backwards to calculate the density of the EBL that caused the absorption. It's like listening to a familiar song playing from a room far away. If you know what the song is supposed to sound like, you can tell how much the high notes have been muffled by the walls and the distance, and from that you can infer the properties of the materials in between. In this case, the song is the intrinsic spectrum of a blazar, which we can often model based on our understanding of jet physics, and the muffling is the absorption by the EBL. This technique provides a unique and crucial measurement. The extragalactic background light is incredibly difficult to observe directly because it is so faint and is drowned out by the brilliant foreground light from our own solar system and galaxy. By using gamma rays as a probe, we can effectively see the shadow that the EBL casts on them. This allows us to measure the total amount of starlight ever produced, offering an independent check on our models of galaxy formation and evolution. Do the number of galaxies we see and their estimated brightness over time add up to the EBL density that gamma-ray absorption tells us is out there? The answers have been remarkably consistent, confirming the broad outline of our cosmic history. However, some intriguing discrepancies remain, hinting that there might be additional, faint sources of starlight that our telescopes have yet to detect, perhaps from the very first galaxies that formed in the universe. The absorption of gamma rays by the EBL is a beautiful example of a cosmic inconvenience transformed into a window of discovery, allowing us to use the most energetic photons to illuminate the faintest glow of all. This smoothness, however, presents a fascinating contradiction that strikes at the very heart of observational astronomy. Given the incredible sensitivity of an instrument like the Fermi telescope, which can pinpoint gamma-ray flashes from the edge of the observable universe, why does a large fraction of this background stubbornly refuse to resolve into distinct points of light? We know the sky is filled with individual sources, blazars, pulsars, gamma-ray bursts, so the natural expectation was that as our telescopes improved, the fog would gradually clear, revealing a sky dense with countless faint emitters. Instead, we've found that a significant portion of the glow remains fundamentally diffuse. This is the puzzle of the missing point sources, and it forces us to confront the fundamental limits of our vision. One compelling explanation is a simple matter of numbers and distance. Imagine standing in a vast, darkened plain, looking toward a distant city. You see the distinct, bright lights of skyscrapers and stadiums. But as your gaze moves to the sprawling suburbs miles away, the individual porch lights and street lamps blend into a uniform, hazy glow. No matter how sharp your eyesight, there is a threshold where the lights become too numerous, too small, and too distant to distinguish from one another. This is likely the situation with the gamma-ray background. The contributing sources aren't missing, they are just beyond Fermi's resolution limit. There could be a truly immense population of incredibly faint blazars or star-forming galaxies so far away that their individual signals are lost in the noise. Each one contributes a minuscule trickle of gamma rays, but collectively, they create a river of light that our current instruments can only perceive as a unified flow. But what if the answer isn't just a matter of faintness? This leads to a second, more profound possibility, that a substantial part of the emission is genuinely diffuse in nature. This means it isn't coming from discrete points at all, but is instead produced by processes that are inherently spread across vast volumes of space. The prime candidate for this is the dark matter hypothesis. If dark matter particles are annihilating throughout the immense halos that surround galaxies and permeate the voids between them, the resulting gamma rays would originate from everywhere at once. There would be no point to focus on because the source is the very fabric of the cosmos itself. Similarly, the proposed emission from the large-scale structure of the universe, the gamma rays generated in the colossal shock waves of the cosmic web, would be fundamentally extended, lacking a sharp, localized origin. In this scenario, the background remains unresolved not because our telescopes are inadequate, but because the sources are, by their very nature, seamless and omnipresent. We must also consider the technical and practical challenges of this cosmic detective work. Distinguishing a faint point source from the surrounding background is an immense statistical challenge. The signals are incredibly weak, and detectors are plagued by background noise, random fluctuations that can mimic the signature of a real source. Astronomers have to set a strict brightness threshold. Any signal below that level cannot be confidently identified as a distinct object and is instead folded back into the diffuse map. It's a constant battle against uncertainty. Furthermore, our own galaxy creates a brilliant and complex foreground of gamma rays, from pulsars to interactions of cosmic rays with gas clouds. Peering through this bright local veil to detect the faint, uniform backdrop of extragalactic light is like trying to study the faintest stars in the sky at high noon. The process of subtracting this foreground is delicate and imperfect, and any errors could leave behind artifacts that masquerade as a truly diffuse extragalactic background. The resolution to this mystery likely lies in a combination of all these factors. The background is probably a composite. A portion comes from the countless faint blazars and galaxies that lie just beyond our current vision. Another portion from the truly diffuse processes like dark matter annihilation or structure formation, all viewed through the imperfect filter of our observational limitations. This makes the quest for the next generation of gamma-ray telescopes so critical. Instruments with significantly improved sensitivity and angular resolution will push that detection threshold fainter, resolving a greater fraction of the fog into individual points. If the diffuse component shrinks dramatically, we'll know the culprit was simply distance. But if a persistent, uniform glow remains even with vastly superior technology, the case for a genuinely diffuse origin, potentially linked to the dark universe, becomes overwhelmingly strong. The missing point sources are not an absence of evidence, but a clue written in negative space, telling us that the universe's greatest secrets are hidden not in its brilliant beacons, but in its quietest hum. But to build a truly complete picture of the gamma-ray sky, we must look beyond the brilliant beacons of blazars and consider their less flashy but far more numerous relatives, radio galaxies. Up to this point, we've focused on the special case where a supermassive black hole's jet is aimed directly at Earth, making it appear exceptionally bright. But what about all the other active galaxies where we're seeing the jet from the side or from an oblique angle? This is the realm of radio galaxies, and their contribution to the cosmic background is a crucial piece of the puzzle, one that highlights the importance of our own cosmic perspective. The fundamental difference lies in geometry. Both blazars and radio galaxies are powered by the same engine, a supermassive black hole feeding on surrounding matter and producing powerful jets. The distinction is purely based on our line of sight. If the jet is pointed almost directly at us, we call it a blazar. But for every one of those, there are many more active galaxies where the jet is pointed in a different direction, perhaps perpendicular to our view or at a steep angle. In these cases, we are not looking straight down the particle accelerator's barrel. Instead, we see the entire structure from the side, the central core, the long, often wiggling jets extending for thousands of light years, and the giant, balloon-like lobes at the ends where the jet material slams into intergalactic space and piles up. These lobes are particularly important because they are vast reservoirs of energy, glowing brightly at radio wavelengths, hence the name radio galaxy, and, as we've discovered, in gamma rays as well. So, how do these misaligned jets produce gamma rays if we're not in the direct path of the most intense radiation? The process is different from the highly beamed emission of a blazar. In a radio galaxy, the gamma rays are thought to arise from a few key regions. First, the giant lobes themselves are filled with relativistic particles and tangled magnetic fields. The electrons in these lobes can upscatter low-energy photons from the cosmic microwave background to gamma-ray energies, a process known as inverse Compton scattering. Secondly, the jets, even when seen from the side, are still powerful conduits of energy. Shock waves and turbulence within the jets can accelerate particles, leading to gamma-ray emission that is less focused but still significant. The key point is that this emission is much more isotropic. It radiates in many directions rather than being concentrated into a narrow beam. This makes each individual radio galaxy much fainter in gamma rays than a blazar, but their sheer numbers could make them a collective force to be reckoned with. Estimating their total contribution becomes a fascinating exercise in cosmic accounting. Radio galaxies are far more common than blazars. Think of it like lighthouses on a rocky coast. A blazar is like a lighthouse whose beam is shining directly into your eyes. It's overwhelmingly bright. A radio galaxy is like a lighthouse you're viewing from the side. You see the light from the tower's windows and the glow reflecting off the surrounding rocks, which is much dimmer but still visible. Now imagine a coastline with hundreds of lighthouses, but only a handful are pointed at you. The total light coming from all the sidelong lighthouses could easily rival or even exceed the combined glare from the few that are aimed your way. Similarly, while each radio galaxy is faint, there are so many of them that their summed, unresolved light could form a substantial part of the gamma-ray background. Detailed models that incorporate the known populations and gamma-ray luminosities of radio galaxies suggest they play a specific and important role. They are generally considered a sub-dominant component, meaning they are unlikely to be the primary source of the background. Their diffuse glow is thought to contribute at a level below that of the unresolved blazar population. However, they are absolutely essential for creating a complete and accurate model of the high-energy sky. Leaving them out would be like trying to calculate the total sound of an orchestra while ignoring the entire string section. You might still hear the brass and percussion, but the overall texture and volume would be wrong. Radio galaxies provide a necessary, smooth underlying component that helps fill in the gaps between the more clumpy signal from blazars. This understanding helps refine the interpretation of the anisotropy, or the lumpiness of the background. The emission from radio galaxies is expected to be less clustered than that from blazars, because their gamma rays are produced in large, extended lobes, and because we see them from random orientations, their contribution to the sky map should be smoother. This characteristic can actually help explain why the observed fluctuations in the background are somewhat lower than what might be expected from blazars alone. The more isotropic glow from the vast population of radio galaxies acts to dilute the patchiness, washing out the sharp statistical signature of the blazars and bringing the models closer in line with what we actually observe. Their quiet, widespread hum is the essential bass note that balances the sharper treble of the blazar population, creating the complex cosmic chord we detect from Earth. While we often picture galaxy clusters as collections of distinct galaxies, there exists a far more ghostly component to these cosmic metropolises: intracluster light. This is the faint, diffuse glow from countless stars that have been gravitationally ripped from their home galaxies during violent encounters and mergers. These stellar orphans now drift freely in the immense spaces between the cluster's galaxies, forming a vast, tenuous fog of suns. For a long time, this light was merely a curious astronomical footnote, but it now emerges as a potential player in the gamma-ray story, not as a direct source but as a crucial catalyst. The connection lies in the interaction between the cosmic rays that fill a cluster and the prodigious amount of ordinary starlight that this intracluster population provides. The process is a specific type of the inverse Compton scattering we've encountered before, but with a unique twist. Recall that cosmic rays, especially high-energy electrons, can collide with low-energy photons and boost them to gamma-ray energies. Within a galaxy cluster, there are two main sources of photons: the relic light from the Big Bang, known as the cosmic microwave background, and the much more recent starlight, including this intracluster glow. The intracluster light is particularly significant because it is far more concentrated and intense than the cosmic microwave background within the cluster's volume. It creates a dense sea of optical and infrared photons right where the cosmic rays are trapped. When a relativistic electron smashes into one of these intracluster light photons, it can impart a tremendous amount of energy, effectively upgrading the photon from visible light into a high-energy gamma ray. This mechanism suggests that galaxy clusters could be generating a faint secondary gamma-ray glow that is directly tied to their history of violence and assembly. The intensity of this signal would depend on two key factors: the density of the cosmic ray population and the brightness of the intracluster light. Clusters that have experienced a lot of recent mergers and activity would have both a rich supply of freshly accelerated cosmic rays and a brilliant intracluster light from all the stars recently stripped away from their galaxies. This makes the signal a potential tracer of a cluster's dynamic past. Detecting it, however, is a monumental challenge. The predicted gamma-ray flux from this process is exceptionally faint, pushing up against the very limits of what our current telescopes like Fermi can perceive. It's like trying to spot the glow of a single candle from thousands of miles away. The significance of this idea is that it adds another layer of subtlety to our models. If this contribution is real, it means that the gamma-ray background isn't just a simple sum of emissions from discrete sources like blazars and star-forming galaxies. It also contains a component that is generated in the vast, empty spaces within the largest structures in the universe, a byproduct of the gravitational chaos that builds galaxy clusters. This intracluster light connection reminds us that the universe is a complex ecosystem where different components, stars, cosmic rays, and light interact in unexpected ways. While its contribution to the all-sky background may be small, studying it could provide a unique new window into the physics of galaxy clusters, allowing us to map their turbulent history by the very faintest glow they cast upon the cosmos. This brings us to a mystery that unfolds not in space but in time itself. We've mapped the gamma-ray background across the sky and analyzed its energy spectrum, but there's another fundamental question: does this faint glow change over time? Is it a perfectly steady hum, unwavering over years or even decades, or does it possess a subtle, rhythmic pulse? The answer to this question of time variability is a powerful diagnostic tool, capable of distinguishing between entire classes of potential sources with a clarity that other measurements struggle to achieve. Consider the nature of the proposed contributors. A source like dark matter annihilation would be the epitome of steadiness. If dark matter particles are spread smoothly throughout the halos of galaxies and the cosmic web, their rate of annihilation would be constant on human timescales. The resulting gamma-ray signal would be as unchanging as the universe's fundamental constants, a perpetual and immutable light. Similarly, the combined light from an unimaginably vast number of faint, distant star-forming galaxies would also produce an exceptionally steady signal. While any single galaxy might have bursts of star formation, the sheer number of contributors, each at a different point in its evolutionary cycle, would average out to a constant glow. It's the cosmic equivalent of the sound from a massive forest. While individual leaves may rustle and individual branches may crack, the overall sound from a billion trees is a steady, unwavering whisper. Now contrast that with the behavior of blazars. These objects are notoriously variable. A blazar can flare up, doubling or even quadrupling its gamma-ray brightness in a matter of hours or days before fading back to its normal state. This variability is a direct result of the chaotic, turbulent processes happening within its relativistic jet. If the unresolved gamma-ray background were dominated by a relatively small number of such blazars, even if they are too faint for us to see individually, their collective signal might not be perfectly smooth. Instead, it could exhibit subtle fluctuations. If a handful of these hidden blazars were to flare up at the same time, they would create a tiny, statistically detectable increase in the overall background flux in a particular region of the sky. It would be like listening to a large crowd. If the crowd is made of millions of people, the overall noise level is constant. But if it's only a few thousand, the sudden shouting of a small group can cause a noticeable, if faint, ripple in the total volume. This is where the observational challenge becomes truly Herculean. Detecting variability in a signal that is already at the absolute limit of our detection capabilities is like trying to measure the minute rise and fall of the ocean's surface during a calm day using a ruler from a mile away. The gamma-ray background is incredibly faint, and any potential variations would be minuscule, buried deep within the statistical noise of the detector itself. Scientists using data from the Fermi telescope must perform a painstaking analysis comparing the total flux year after year and even season after season, searching for any systematic shift that rises above the random chatter of the instrument. They have to meticulously account for known variable sources, ensuring that a bright, near-by blazar having an outburst doesn't contaminate the measurement of the truly diffuse background. It is a search for a ghost of a signal within a sea of uncertainty. The results of this meticulous work have been both conclusive and intriguing. To date, no significant variability has been detected in the extragalactic gamma-ray background. The signal appears to be remarkably steady over the more than a decade that Fermi has been observing. This null result is a profound piece of evidence. It strongly disfavors models where the background is dominated by a small population of relatively bright, variable blazars. The steadiness is much more consistent with a scenario involving either a truly enormous number of faint sources, like the unresolved blazar population or star-forming galaxies, or a fundamentally steady process like dark matter annihilation. However, the absence of evidence is not evidence of absence. The steadiness we observe is over a specific time frame, roughly 15 years. Could there be variability on much longer timescales, perhaps centuries or millennia, that we simply cannot yet detect? Or what about incredibly short, transient fluctuations that are too rapid for our current instruments to catch? The steady signal we see today places critical constraints on our models, forcing us to favor explanations that are stable over human timescales, but it also leaves the door open for more complex theories. Perhaps the background is a composite with a large, steady component from faint galaxies and a smaller, variable component from blazars that is simply too subtle for us to detect against the dominant, unwavering hum. The search for time variability continues, a patient, long-term project that requires the sustained gaze of our telescopes. Each passing year of data adds another point to the light curve of the universe, tightening the constraints and bringing us closer to understanding the timeless, or perhaps time-bound, nature of the cosmos's hidden light. To truly grasp the origin of this faint gamma-ray fog, we need to follow the trail of energy back one step further to the very particles that often create it. Cosmic rays are the invisible bullets of deep space, primarily protons and atomic nuclei accelerated to almost the speed of light. They are not gamma rays themselves, but they are the master architects, the powerful progenitors that build the high-energy light we eventually detect. The connection lies in the fundamental principle that energy is never lost, only transformed. When these ultra-fast particles slam into something, a cloud of gas, a photon of light, their immense kinetic energy is converted into new forms, and a frequent byproduct of this violent transformation is the creation of gamma-ray photons. This makes the journey of cosmic rays and how they travel across the universe a critical piece of the background puzzle. The process works through several key channels. The most direct is when a cosmic ray proton collides head-on with a proton in a stationary gas cloud. This collision can create a short-lived particle called a neutral pion, which almost instantly decays into two gamma rays. This is the primary way gamma rays are produced within our own Milky Way and in other star-forming galaxies. But there's another, more subtle process that becomes crucial in the vast, empty expanses between galaxies. Cosmic rays are not just protons, a fraction are high-energy electrons. When these relativistic electrons encounter low-energy photons, like those from the cosmic microwave background or the diffuse starlight that fills the universe, they can boost these humble photons to gamma-ray energies through a mechanism known as inverse Compton scattering. It's like a cosmic game of pool where a fast-moving electron smashes into a slow-moving photon, transferring so much energy that the photon is rocketed into the gamma-ray part of the spectrum. This is where the concept of propagation becomes paramount. We often think of cosmic rays as being generated in specific locations, like supernova remnants within galaxies. But once created, they don't stay put. They are propelled by magnetic fields that weave through intergalactic space, diffusing out of their home galaxies and traveling across millions of light years. This means the entire universe is permeated by a diffuse sea of these energetic particles. As they wander this cosmic ocean, they continuously interact with the sparse medium they find, the tenuous gas of the intergalactic medium and the omnipresent bath of background light. Every one of these interactions is a potential gamma-ray factory. The cumulative effect of trillions upon trillions of these tiny, widespread events happening all across the cosmos could very well produce a faint, uniform glow that adds to the gamma-ray background we observe. This idea dramatically broadens the scope of our investigation. It suggests that the background isn't just a census of distant sources like blazars, but also a reflection of the dynamic life of particles traveling through the architecture of the universe itself. The intensity of this component would depend on two major factors: the density of cosmic rays in intergalactic space and the density of the targets they interact with. This creates a fascinating link to the large-scale structure of the cosmos. Cosmic rays should be more concentrated along the filaments of the cosmic web, where matter is denser, and their gamma-ray production would be enhanced in these regions. Conversely, in the immense voids where matter is scarce, the signal would be much weaker. This could potentially imprint a very faint web-like pattern onto the gamma-ray background, a pattern that would be incredibly difficult to detect but would be a direct map of the cosmic rivers of matter and energy. Understanding this process also forces us to consider the incredible journeys these particles undertake. A cosmic ray ejected from a galaxy several hundred million light-years away must travel through a hostile environment. The expanding universe stretches its wavelength, and the particle itself can lose energy through these very interactions that produce gamma rays. By the time it contributes to the diffuse glow we see, it has a long and complicated history. Modeling this propagation is a formidable challenge for physicists, requiring complex simulations that track magnetic fields, particle interactions, and the evolving structure of the universe over billions of years. The predicted gamma-ray signal from this intergalactic cosmic ray population is expected to be faint, likely a secondary component compared to the unresolved light of galaxies. However, it represents a fundamental and inescapable part of the high-energy universe's ecosystem. It reminds us that the cosmos is not just a collection of discrete objects, but a connected system where energy and matter flow from one region to another, leaving a trace of their passage in the form of a silent, universal glow. Now we turn our attention to the outermost frontier of energy, where the gamma-ray background spectrum confronts a fundamental limit. As we push our observations to the very highest energies, we encounter a critical mystery. Does this faint glow simply fade away gradually, or is there a sudden, sharp cutoff, a point beyond which the light of the universe simply stops? The answer to this question is not just a detail on a graph. It acts as a final, stringent test for our theories, probing the ultimate capabilities of cosmic engines and the true transparency of the cosmos. To understand why a cutoff might exist, we need to consider the two competing forces at play: production and destruction. On one hand, there is the question of whether any physical process in the universe can even accelerate particles to energies high enough to produce such tremendously powerful gamma rays in the first place. Every known accelerator, from the shock waves of a supernova remnant to the relativistic jets of a blazar, has a theoretical maximum. There's only so much energy these natural machines can impart to a proton or electron before physical limits, like energy loss mechanisms or the sheer size of the accelerator, prevent it from going any faster. If the highest energy gamma rays are produced when these ultra-fast particles collide, then the maximum energy of the gamma rays themselves is directly capped by the maximum energy of the particles that create them. A sharp cutoff in the background spectrum could therefore be a direct reflection of nature's ultimate speed limit for particle acceleration, a signature of the most powerful engines the universe can build. On the other hand, even if such extreme gamma rays are produced, their journey to our telescopes is a perilous one. This is where the extragalactic background light, that cosmic fog of ancient starlight, plays its most dramatic role. The probability that a high-energy gamma ray will be annihilated by a collision with a low-energy EBL photon increases tremendously as the gamma ray's energy increases. At a certain threshold energy, the universe effectively becomes opaque. The mean free path of the photon, the average distance it can travel before being absorbed, drops to a value smaller than the cosmological distances it must traverse. For gamma rays at the tera-electronvolt scale and beyond, the universe is no longer a clear window. It is a dense, absorbing wall. A sharp cutoff observed in the spectrum of the diffuse background would be the direct imprint of this universal veil, the shadow cast by the total accumulated starlight of all time. Distinguishing between these two possibilities, an intrinsic limit of the sources versus a blanket of absorption, is one of the most delicate challenges in high-energy astrophysics. The observed spectrum we measure is the final product after all the physics of creation and destruction has played out. If we see a steep drop-off, is it because the sources have run out of power or because the EBL has filtered out their most energetic light? To tell the difference, scientists use our knowledge of nearby sources as a calibration tool. We can study individual blazars within our own cosmic neighborhood, whose light travels a relatively short distance through the EBL fog. By understanding their intrinsic, unabsorbed spectra at high energies, we can better model what more distant versions of these objects should look like before their light is processed by the intervening space. Any discrepancy between that prediction and what we actually see from the diffuse background at the highest energies points squarely to the effect of absorption. The search for this cutoff is pushing our observational capabilities to the absolute brink. Detecting photons at these extreme energies is incredibly difficult because they are exceedingly rare. Telescopes like the Fermi LAT are optimized for a broad range, but to probe the very highest energies, we often rely on ground-based instruments like imaging atmospheric Cherenkov telescopes. These detectors don't observe the gamma rays directly. Instead, they capture the brief, faint flashes of blue Cherenkov light produced when a gamma ray slams into the Earth's atmosphere and creates a cascade of secondary particles. It's an indirect method, and mapping a diffuse, faint background with such techniques is extraordinarily challenging. The signal is buried in a sea of background noise from other cosmic rays. The implications of finding a definitive cutoff are profound. If it aligns perfectly with predictions from EBL absorption models, it would provide a stunning confirmation of our understanding of the total history of starlight in the universe. It would mean we have accurately accounted for the light from every galaxy, every star across all of cosmic time. Conversely, if the cutoff occurs at an energy higher than expected, it could suggest that the EBL is less dense than we think, perhaps hinting that our census of faint, early galaxies is incomplete. If the cutoff is lower than predicted, it might indicate that our theories of particle acceleration are flawed, or that there is an additional, unknown source of absorption in the universe. The high-energy frontier is where our models are stress-tested most severely, and any deviation from expectation is a potential signpost to new physics, pointing toward phenomena we have not yet even begun to imagine. This brings us to a sophisticated detective technique that allows us to see the invisible, not by looking harder at the gamma rays themselves, but by comparing their map to the universe as seen through different eyes. When a single witness gives a hazy description, the story remains unclear. But when you combine that account with the testimony of several other independent witnesses, a much sharper picture begins to emerge. This is the power of cross-correlation, a method that statistically compares the faint, patchy texture of the gamma-ray background with incredibly detailed maps of the cosmos created at other wavelengths, from the infrared glow of dust to the radio whispers of cold gas or even the subtle distortions of space-time caused by gravity. The underlying logic is beautifully simple yet profound. If a particular type of object is responsible for generating a portion of the gamma-ray background, then the distribution of that glow on the sky should subtly match or correlate with the distribution of those objects. Imagine you're looking at a photograph of a forest at night, but the image is so dark and grainy that you can only see a faint, mottled pattern of light and shadow. You suspect the pattern is caused by fireflies, but you can't be sure. Now, imagine you also have a thermal image of the same forest, showing the warm bodies of all the animals. If you overlay the two images and find that the faint glowing patches in your dark photo consistently overlap with the locations of the warm animals, you have strong evidence that the light is indeed coming from bioluminescent creatures and not from some other source like faint reflections off leaves. Cross-correlation in astronomy works on the same principle, but on a cosmic scale. One of the most significant correlations studied is between the gamma-ray map and traces of the large-scale structure of the universe. Astronomers create these maps using massive surveys that catalog the positions of millions of galaxies in the infrared or optical. These galaxies are not randomly scattered. They trace out the cosmic web, concentrating along vast filaments and in dense clusters. When scientists perform a statistical cross-correlation, they have found a clear positive signal. The faint fluctuations in the gamma-ray background are indeed more likely to align with the regions of sky that are densely packed with galaxies. This is a monumental result. It definitively tells us that the sources of the background are not smoothly distributed like a perfectly mixed gas. They are clustered in a way that mirrors the visible matter in the universe. This finding strongly supports the idea that the dominant contributors are astrophysical objects like blazars and star-forming galaxies, which are known to reside within galaxies and clusters, rather than a perfectly smooth component like a specific dark matter signal that might permeate even the empty voids. An even more powerful and revealing correlation comes from comparing the gamma-ray sky with maps of gravitational lensing. This technique doesn't rely on light at all, but on the very fabric of space-time itself. As light from distant galaxies travels across the universe to reach us, its path is subtly bent by the gravitational pull of all the matter, both visible and dark, that it passes along the way. This warping causes tiny, systematic distortions in the shapes of billions of background galaxies. By meticulously measuring these distortions, astronomers can create a map of the total mass distribution in the universe, a map that primarily reveals the hidden scaffolding of dark matter. This is a direct view of the cosmic web's gravitational skeleton. When researchers cross-correlated the Fermi gamma-ray background map with these dark matter maps from gravitational lensing surveys, they made a fascinating discovery. They found a significant correlation. The patches of the sky with a slightly higher gamma-ray intensity tended to overlap with the regions where the gravitational lensing signal was stronger, meaning where the dark matter is more concentrated. This might seem to immediately point to dark matter annihilation as the source. However, the interpretation requires careful nuance. Remember, we already know from the galaxy correlation that astrophysical sources are clustered. And galaxies themselves, of course, reside within the very same dark matter halos that the lensing maps are revealing. So, the correlation with lensing could simply be a secondary effect. The gamma rays are coming from the galaxies inside the dark matter halos, not from the dark matter itself. The challenge for scientists is to disentangle this. They look at the precise strength and scale of the correlation. If the gamma-ray signal were coming directly from dark matter annihilation, the correlation might be stronger on very large scales, tracing the full extent of the diffuse dark matter halos. The current data suggests the correlation is more consistent with the gamma rays originating from the relatively compact galaxies embedded within the halos, providing yet more weight to the astrophysical explanation. These cross-correlation studies represent a fundamental shift from simply cataloging what we can see to intelligently inferring the nature of what we cannot see directly. Each new wavelength map we compare, from the X-ray glow of hot gas to the radio emission from neutral hydrogen, adds another layer of testimony. A strong correlation with infrared light, which marks regions of intense dust-obscured star formation, would bolster the case for star-forming galaxies as a major contributor. A lack of correlation with a particular type of object can be just as telling, allowing us to rule out certain candidates. This multi-messenger approach to the gamma-ray background is transforming it from an impenetrable fog into a complex cryptographic message. We may not be able to read each individual character yet, but by seeing how the patterns align with other known texts, we are slowly beginning to decipher the story of the high-energy universe and the invisible structures that define it. Amidst the intricate tapestry of faint variations and statistical clues, there is a concept that helps us separate the signal from the noise in a profound way: the idea of an isotropic minimum. Think of it as searching for the baseline hum in a vast, echoing chamber. Even after you've identified all the distinct voices and the subtle rustling from different corners, there remains a fundamental, underlying tone that seems to come from everywhere at once with no discernible source. This is the isotropic minimum in the gamma-ray sky, a level of flux so incredibly smooth and uniform that it appears to have no structure whatsoever. It represents the floor of the background, the portion that stubbornly resists all attempts to link it to any known clumpy distribution of matter, and it may well be our clearest window into the most remote and ancient reaches of the cosmos. Distinguishing this minimum from the anisotropic, or lumpy, parts of the signal is a bit like analyzing a pointillist painting. Up close, you can see the individual dots of color, the distinct brushstrokes that create the image. These are the anisotropic fluctuations, the statistical signature of sources like unresolved blazars that trace the large-scale structure of the universe. But if you step far enough back, those individual points blend into a uniform wash of color that forms the painting's background. This underlying wash is the isotropic minimum. Scientifically, researchers isolate it by applying ever more sensitive filters to the gamma-ray map, mathematically smoothing out the fluctuations until all that remains is a signal with no correlation to the positions of galaxies or dark matter halos. It is the residue of the residue, the most fundamental and enigmatic component of the glow. What could produce such perfect uniformity? One compelling explanation points to the very edge of the observable universe. This minimum could be the collective light from the first generations of gamma-ray sources, so incredibly distant that their individual signals are completely blurred by the expansion of spacetime itself. The expansion stretches the wavelengths of their light and smears their positions across the sky, blending their contributions into a seamless, omnipresent fog. These sources would be from a time when the universe was in its infancy, perhaps populated by the earliest supermassive black holes or a primordial population of stars so massive and short-lived that their deaths were titanic gamma-ray factories. Because this light has traveled for nearly the entire age of the universe, it carries an imprint from an epoch that is otherwise incredibly difficult to observe directly. Alternatively, this minimum might not come from discrete sources at all, but from a process that is genuinely diffuse. This is where exotic possibilities like particle decay come into sharp focus. Imagine if a fundamental particle that permeates all of space, a relic from the Big Bang like the neutrino, but much heavier, were slowly, steadily decaying over billions of years. Each decay event would release a gamma ray. Since these particles would be distributed almost perfectly evenly throughout the cosmos, the resulting gamma-ray signal would be the very definition of isotropic. It would be a true universal background, a fossil glow not from stars or galaxies, but from the quantum decay of the vacuum of space itself. Another candidate is the cumulative emission from the vast, empty voids between galaxy clusters. While these regions are relatively barren, they still contain a sparse population of cosmic rays and background light. The interactions between them, happening across unimaginably large volumes, could generate a faint, uniform glow that contributes to this minimum level. The value of this isotropic flaw is not just in its existence, but in its intensity. The precise level of this minimum flux acts as a crucial constraint for our models of cosmic history. If it is very high, it suggests that the early universe was a far more violent and productive place in gamma rays than we currently understand, teeming with energetic processes we have yet to identify. If it is surprisingly low, it might indicate that our universe becomes opaque to gamma rays sooner than expected, or that the mechanisms for particle acceleration in the primordial cosmos were less efficient. By measuring this baseline, we are essentially taking the temperature of the universe's high-energy activity averaged over all of space and time. It is a single number that encapsulates the total gamma-ray luminosity of the cosmos, a number that any complete theory of galaxy formation, dark matter, and particle physics must ultimately reproduce. Pinpointing the isotropic minimum is therefore one of the ultimate goals in this field, a fundamental measurement that separates the local chatter of the universe from its deepest, most universal whisper. Of all the obstacles standing between us and a clear understanding of the cosmic gamma-ray background, perhaps the most formidable one is much closer to home. In fact, it's our entire home galaxy. The Milky Way is not a passive window through which we view the distant universe. It is an active, brilliant source of gamma rays in its own right, creating an intense and complex foreground that completely obscures the faint extragalactic signal we're trying to study. Imagine trying to observe the faint, distant lights of a city on the far horizon, but you're standing in the middle of a brilliantly lit sports stadium at night. The glare from the stadium lights is so overwhelming that it drowns out everything else. That's precisely the challenge posed by our galaxy's own gamma-ray emission. Before we can even begin to analyze the whisper from across the cosmos, we must first find a way to subtract the roar coming from our own galactic neighborhood. So, where does all this local light come from? The primary source is the vast sea of cosmic rays that fills the Milky Way. These high-energy particles, accelerated by supernova explosions and pulsar wind nebulae, are confined by the galaxy's magnetic fields, continuously zipping through the immense clouds of gas and dust that drift between the stars. When a cosmic ray proton collides with a proton in a hydrogen gas cloud, the interaction can produce a neutral pion, which then rapidly decays into two gamma rays. This process turns the entire interstellar medium into a gigantic, diffuse gamma-ray glow. The intensity of this emission isn't uniform. It's brightest along the plane of the Milky Way, where stars and gas are most densely packed, and it traces out the spiral arms and giant molecular clouds that serve as the galaxy's star-forming factories. Beyond this dominant process, there are also distinct point sources scattered across the galactic foreground, pulsars blinking with lighthouse-like regularity, the expanding shells of supernova remnants, and the mysterious, extended glow of pulsar wind nebulae. Each of these contributes its own sharp signature to an already complex picture. The task of removing this galactic foreground is one of the most delicate and sophisticated procedures in all of astronomy. It's not as simple as just blocking out the bright band of the Milky Way. The galactic emission is not a simple, uniform curtain. It's a three-dimensional, dynamic structure. To model it, scientists must create a virtual Milky Way inside a supercomputer. This model incorporates our best maps of the galaxy's interstellar gas, built from radio telescopes that measure the emission from neutral hydrogen and carbon monoxide. It includes a model of the distribution and energy spectrum of galactic cosmic rays, and it uses our understanding of particle physics to simulate the gamma-ray glow that should result from the interactions between these cosmic rays and this gas. The result is a predicted all-sky map of what the Milky Way should look like in gamma rays based purely on physics. Researchers then painstakingly compare this simulated map to the actual data from the Fermi telescope, adjusting the model's parameters until it fits the observed emission as perfectly as possible. Only then can they subtract this best-fit model away, hoping to reveal the faint, uniform extragalactic background that lies behind it. This process, however, is fraught with peril and uncertainty. The models are only as good as the data we put into them. Our maps of the galactic gas are incomplete, especially for the coldest, densest molecular clouds that are prolific gamma-ray producers. Our understanding of how cosmic rays propagate through the galaxy's magnetic fields is still evolving. Small errors or oversimplifications in the foreground model can have dramatic consequences for the final measurement of the background. If the model underestimates the true galactic emission in a particular patch of sky, then after subtraction, that patch will appear artificially dark, creating a false dip in the background map. Conversely, if the model overestimates the foreground, the subtraction will leave behind a false, positive residual that could be mistaken for a genuine feature of the extragalactic signal. These imperfections are the hidden systematic uncertainties that lurk behind every published measurement of the gamma-ray background's intensity and anisotropy. The ghost of our own galaxy can subtly haunt the data, potentially leading us to misinterpret the faint whispers from the deep universe. This galactic foreground challenge is a humbling reminder that to see the cosmos clearly, we must first understand our own place within it with exquisite precision. Yet, for all the cosmic engines and dark matter candidates we have considered, there remains a possibility so profound that it would dwarf all other explanations. This is the chance that the gamma-ray background is not just a map of astrophysical objects or hidden matter, but a direct message from a realm of physics we have not yet discovered, a signature of laws that operate beyond our current standard model of particle physics. While extraordinarily speculative, this idea forces us to confront the ultimate limits of our knowledge and consider that the universe might be whispering clues about its most fundamental workings in this faint, high-energy static. Our standard model is a masterpiece of human intellect, a framework that brilliantly describes the particles and forces that make up the world we see. But for all its success, it is glaringly incomplete. It cannot explain the nature of dark matter, the force driving the universe's accelerated expansion known as dark energy, or why gravity is so weak compared to the other forces. It is a theory that explains the content of the universe, but not its deepest mysteries. The gamma-ray background could act as a testing ground for the ideas that seek to fill these gaps. If new particles or forces exist, they might leave an imprint in the high-energy sky through their creation, interaction, or decay. Unlike the focused search for a dark matter signal, this broader hunt looks for any anomaly in the data that stubbornly resists explanation by any known astrophysical or particle physics process. It is a search for the truly unknown. One compelling avenue involves the concept of particle decay on a cosmological scale. The standard model includes stable particles like the proton, but many theories that extend it predict the existence of massive, long-lived particles that were created in the extreme heat of the Big Bang. If such a particle exists, and if it slowly decays over the lifetime of the universe, each decay event could produce a cascade of secondary particles, including gamma rays. Because these primordial particles would have been spread evenly throughout the cosmos during its infancy, their decay would produce a perfectly isotropic, uniform glow of gamma radiation, a potential component of the background's mysterious isotropic minimum. The energy spectrum of this glow would carry the fingerprint of the parent particle's mass, offering a direct way to measure the properties of something that has existed since the first moments of time. Even more mind-bending are the possibilities tied to the concept of extraspatial dimensions. Some theories, like string theory, propose that the universe has more than the 3 dimensions of space we experience. These extra dimensions could be curled up or compactified, too small for us to perceive directly. However, their existence could have dramatic consequences. For instance, if gravity is able to leak into these extra dimensions, it could explain why it appears so weak in our 3-dimensional world. The creation and evaporation of microscopic black holes, or the vibrations of fundamental strings, processes tied to these higher dimensions, could potentially produce unique signatures in the gamma-ray spectrum. We might be seeing the high-energy fallout from events occurring in a reality with more layers than we can possibly imagine. Furthermore, the gamma-ray background could even hold a fossil record from the epoch of cosmic inflation, the period of fantastically rapid expansion thought to have occurred a fraction of a second after the Big Bang. While inflation is a cornerstone of modern cosmology, the particle physics that drove it is entirely unknown. The energy scale of inflation was unimaginably high, and the violent process of the universe's expansion could have generated a background of gravitational waves, and potentially, primordial gravitational waves could have interacted with the early universe's plasma to generate electromagnetic radiation, including gamma rays. While this signal would be incredibly faint and red-shifted, its unique statistical properties might still be encoded in the patterns of the gamma-ray background, offering an indirect window into the physics of the universe's very birth. The challenge, of course, is monumental, proving that a particular feature in the background is evidence of new physics rather than an unknown type of galaxy or a subtle error in our foreground modeling requires an immense burden of proof. Scientists must systematically rule out every conceivable astrophysical explanation before they can even begin to claim a discovery of new fundamental laws. This process involves relentless cross-checking with observations at other wavelengths and increasingly sophisticated theoretical modeling. The history of science is littered with anomalies that initially seemed revolutionary but were later explained by more mundane causes. Yet, this rigorous skepticism is what makes the potential discovery so powerful. If a signal survives this gauntlet of scrutiny, it would not just be a new fact, it would be a paradigm shift, a key that unlocks a deeper understanding of reality itself. The gamma-ray background, therefore, stands as one of the most sensitive and far-reaching laboratories we have, a place where the subtle fingerprints of the cosmos's ultimate laws may be waiting, hidden in plain sight. As we navigate this intricate labyrinth of possibilities, from unresolved galaxies to the ghostly decay of primordial particles, it becomes clear that our current view of the gamma-ray sky is like an impressionist painting viewed from just a few inches away. We can see the broad strokes and some bold colors, but the true picture, the fine details that reveal the artist's hand, remain blurred. The key to bringing this cosmic masterpiece into focus lies not just in better theories, but in a new generation of eyes on the sky, telescopes so advanced they will transform this faint static into a high-definition map of the high-energy universe. The future of this field is being forged in the designs of revolutionary observatories that will peer deeper and see clearer than ever before. Leading this charge is the Cherenkov Telescope Array, or CTA, an ambitious project that represents a quantum leap in our ability to see the universe's most powerful phenomena. Unlike space-based telescopes like Fermi, which directly detect gamma rays, the CTA is a ground-based observatory that uses a clever, indirect method. It won't catch the gamma rays themselves. Instead, it will detect the fleeting flashes of blue Cherenkov light produced when these high-energy photons slam into the Earth's atmosphere and create a cascade of secondary particles. This technique allows the CTA to access gamma rays at energies far beyond the reach of current instruments, opening a window to the most extreme processes in the cosmos. But its true power lies in its scale and design. Imagine moving from a single security camera to a wall of hundreds of high-resolution cameras working in unison. The CTA will consist of over 100 telescopes of 3 different sizes spread across 2 sites in the northern and southern hemispheres. This array approach provides an unprecedented combination of sensitivity, a wide field of view, and exquisite angular resolution. It will see fainter sources, pinpoint their locations with incredible accuracy, and capture their variations in brightness with a detail that is simply impossible today. This leap in capability will directly tackle the core mystery of the unresolved background. The CTA's superior sensitivity is expected to resolve a significantly larger fraction of the diffuse glow into individual point sources. Thousands of faint blazars and star-forming galaxies that currently blend into the cosmic fog will be pulled into sharp relief, their distinct light subtracted from the background map. This will allow scientists to perform a much more precise cosmic accounting. If the background's intensity drops dramatically as these new sources are identified and removed, we will have strong evidence that the puzzle is primarily one of distance and sensitivity, solved by a larger telescope. However, if a persistent, smooth glow remains even after this deeper census, the case for a genuinely diffuse origin, such as dark matter annihilation or emission from the cosmic web, becomes immensely more compelling. The CTA will also measure the anisotropies, the faint patchiness of the background, with a precision that could finally distinguish between the clustering patterns of different source populations, effectively taking the fingerprint of the hidden universe with forensic clarity. While the CTA explores the highest energies from the ground, a complementary revolution is planned for space. The Advanced Telescope for High-Energy Astrophysics, Athena, is a flagship X-ray observatory mission led by the European Space Agency. While its primary focus is the hot, energetic universe seen in X-rays, its contributions to the gamma-ray background mystery will be profound and indirect. Athena will study the environments around supermassive black holes with unparalleled detail, probing the physics of accretion disks and jets. By understanding the fundamental mechanics of how black holes power their jets, we can build far more accurate models of what the gamma-ray emission from millions of distant blazars should look like. Is the energy output we assume for these objects correct? How does it evolve over cosmic time? Athena's observations will provide the critical empirical data to refine these models, reducing the uncertainties that currently plague our interpretations of the gamma-ray sky. It will be like providing a musicologist with a perfect recording of a single instrument, allowing them to then pick out its sound with confidence from within a complex symphony. The combined power of these observatories will turn the spectrum of the background from a smooth, enigmatic curve into a landscape rich with potential features. The CTA's ability to measure the high-energy cutoff with precision will rigorously test our models of cosmic transparency and particle acceleration limits. It will search for the spectral lines or bumps that could be the smoking gun of dark matter annihilation. The statistical power of its observations will be so great that even the non-detection of a dark matter signal will be profoundly informative, allowing physicists to rule out entire classes of candidate particles and narrowing the search for what makes up the majority of matter in the cosmos. We are on the cusp of a new era where the cosmic gamma-ray background will cease to be a uniform fog and will instead become a dynamic and informative dataset. The whispers we hear today will soon become a chorus of distinct voices, each telling its own story about black holes, stellar explosions, dark matter, and perhaps phenomena we have not yet even dreamed of. The next decade of observation promises to transform our understanding of the universe at its most violent and energetic, finally illuminating the secrets written in light we cannot see. After exploring these individual puzzles, it becomes strikingly clear that we are not dealing with a simple list of separate questions, but rather a single, grand mystery viewed through 25 different lenses. Each piece of the puzzle is locked tightly to the others, and a breakthrough in one area sends ripples across the entire investigation, tightening constraints and opening new possibilities elsewhere. This is not a collection of isolated problems. It is an interconnected web where pulling on one thread inevitably tugs on many others. The true challenge of the gamma-ray background is that it demands we become masters of synthesis, weaving together insights from astrophysics, particle physics, and cosmology into a single, coherent picture. Consider the elegant dance between the sources we can barely see and the signal we cannot explain. The debate over whether unresolved blazars can account for the entire background is intimately tied to the subtle patterns of anisotropy, the faint lumpiness in the glow. If future observations with telescopes like the CTA reveal that the anisotropy is perfectly consistent with the clustering of galaxies, it would strongly suggest that blazars are indeed the dominant player. But that conclusion would immediately shrink the room left for a dark matter signal, pushing the hunt for WIMP into a narrower and more challenging corner. Conversely, if a persistent, perfectly smooth component, the isotropic minimum, remains even after every conceivable astrophysical source is accounted for, the case for a diffuse origin like dark matter annihilation or particle decay suddenly becomes far more compelling. The anisotropy measurement is not just a statistic, it is a scale that weighs the relative contributions of the clumpy universe of galaxies against the smooth universe of dark matter. This interplay extends to the very energy of the light we observe. The high-energy cutoff of the spectrum is a perfect example of a single observation with multiple, interdependent interpretations. A detected cutoff could be telling us about the ultimate power limits of cosmic accelerators like blazar jets, which directly impacts our models of how those jets work. But that same cutoff is also shaped by the thickness of the extragalactic background light, the cosmic fog that absorbs these high-energy photons. To understand if the cutoff is due to the sources running out of steam or the universe becoming opaque, we need independent measurements of the EBL, which themselves rely on our understanding of galaxy evolution across cosmic time. A discrepancy here might not point to a problem with particle acceleration, but rather to a missing population of faint, early galaxies that contribute to the EBL in a way we hadn't predicted. The spectrum, therefore, is a conversation between the physics of the sources, the content of the universe, and the fundamental transparency of space. This holistic approach forces us to see the cosmos as a single, interconnected system. The gamma-ray glow from star-forming galaxies is powered by cosmic rays, which are themselves accelerated in supernova remnants and pulsar wind nebulae. The efficiency of this process in a distant galaxy affects its contribution to the background, which in turn influences how much flux is left to be explained by something else. Even the proposed emission from the large-scale structure of the universe is tied to the gravitational pull of dark matter, which governs how that structure forms. There is no clean separation. A cosmologist studying the growth of the cosmic web, an astrophysicist modeling a blazar's jet, and a particle physicist searching for dark matter are all, perhaps unknowingly, working on different facets of the same profound problem. The gamma-ray background is the meeting point for these disciplines, a common dataset that challenges each field to reconcile its theories with the others. Ultimately, this interconnectedness is what makes the mystery so captivating and so difficult. It means that a simple, single-bullet answer is unlikely. The final explanation will almost certainly be a complex cocktail, a precise recipe detailing the contributions of blazars, radio galaxies, star-forming galaxies, and potentially a sprinkle of dark matter or even new physics. Unmixing this cocktail requires a coordinated effort across all fronts. Better models of galaxy evolution inform the star-forming galaxy contribution, which refines the anisotropy analysis, which constrains the blazar population, which tightens the limits on dark matter. It is a virtuous cycle of discovery where progress in one domain catalyzes progress in another. The 25 mysteries are not hurdles to be cleared one by one. They are threads in a magnificent tapestry. To see the full picture, we must learn to appreciate how each color and fiber blends with the others, creating a unified vision of the universe at its most extreme. And so, our journey through the 25 mysteries of the cosmic gamma-ray background brings us to a final, breathtaking realization. This faint, omnipresent glow is far more than a simple static. It is the universe's ultimate archive, a collective memory written in the language of pure energy. Every photon in this fog is a messenger carrying a story from a cataclysmic event, a dying star, a jet from a voracious black hole, or perhaps the ghostly signature of dark matter itself. We have seen how this light is a complex tapestry woven from countless threads, the unresolved choir of distant blazars, the steady hum of star-forming galaxies, the echoes of gamma-ray bursts, and the tantalizing possibility of physics beyond our current understanding. Each mystery we've explored, from the subtle anisotropies to the high-energy cutoff, is not an isolated puzzle but a different window into the same grand cosmic narrative, a story of creation, destruction, and the invisible forces that shape everything. Unraveling this archive is a testament to human curiosity and ingenuity. It requires us to build instruments like the Fermi telescope and the future Cherenkov telescope array, pushing the boundaries of technology to see the unseen. It demands that we become cosmic detectives, using techniques like cross-correlation to compare the gamma-ray sky with maps of galaxies and dark matter, slowly teasing apart the ingredients of this universal cocktail. The greatest takeaway is that the cosmos is profoundly interconnected. The study of the gamma-ray background is not a niche field. It is a meeting point for cosmology, astrophysics, and particle physics, where understanding the life cycle of a star in a distant galaxy directly informs our search for the fundamental constituents of reality. This faint glow challenges us to think bigger, to see the universe not as a collection of separate objects, but as a single, dynamic system where energy flows from the largest scales to the smallest particles. As we stand on the precipice of new discoveries with next-generation observatories, we are poised to transform this faint whisper into a clear voice. The mysteries that remain are not dead ends, they are guideposts pointing toward a deeper truth about the nature of dark matter, the validity of new physics, and the violent history of the cosmos from its first moments to the present day. Unlocking these secrets will do more than just fill in blanks in our textbooks. It will fundamentally reshape our conception of reality, revealing our place in a universe that is far more extreme, more mysterious, and more wonderfully complex than we ever imagined. The silent storm of gamma rays continues to rage overhead, an endless downpour of questions waiting for us to learn how to listen. We want to hear from you which of these 25 mysteries captures your imagination the most. Is it the potential whisper of dark matter, the power of unseen blazars, or the mind-bending possibility of cosmic strings? Share your thoughts in the comments below, and if you've enjoyed this deep dive into the cosmos's greatest puzzles, be sure to subscribe for more journeys to the edge of our understanding.